All right, so the given information here, the radius of this turntable is 60 centimeters, and the coin is placed right at the edge of it, so we can assume that the coin's circular motion is going to have a radius of 60 centimeters, which I'm going to convert to meters to go into SI units. And then we're given the coefficient of static friction between the coin and turntable, 0.36. So basically, the nephew is supposed to spin the table. He spins it maybe slowly at first, and the coin just moves along with the table as it's spinning. But the nephew's going to try to make it spin faster and faster, and eventually, when the table is spinning fast enough, the coin will not be able to stay on the table. It'll slide off. So what's keeping it on the table is static friction. That's what is preventing it from flying off the table. So this question's a little not as physically realistic because it seems like the child would have to make the table spin faster and faster and faster until the coin does fall off, which means that it's not exactly uniform circular motion. But we're just going to solve it as if it was. Okay, so we're going to ignore that. We're going to assume that, how about the nephew increases the speed of the table like really slowly, so that extra added speed is barely anything, so that most of the time the coin is in uniform circular motion. We'll just have to assume that's what's happening and use uniform circular motion as the approximation. So I kind of write that down. Assume approximately uniform circular motion. All right, so if we're going to assume uniform circular motion, so the coin's just moving in circles, and we know that for uniform circular motion, there has to be a centripetal force, a centripetal acceleration. And what is providing this coin with a centripetal force? Well, it's got, this can be the coin, it's got a little gravity, that's down. It's got a little normal force, that's up, and they're going to be balanced out. But neither of those is going to provide the centripetal acceleration. What's going to provide the centripetal acceleration? Well, that's going to be static friction. Just like the when we talked about the car going around the curve, it was actually static friction providing that centripetal force. The same thing for this coin moving around in circles. So basically, since they tell us the coefficient of static friction, we can calculate what the maximum value of static friction is. That'll be mu times normal force, which is going to be mu times mg, because in this situation, the normal force is equal to the magnitude of the force of gravity. They're balanced. So you can calculate that out. Well, maybe not actually, because I don't know the mass of this coin. All right, so let's go back a little bit here. That's the maximum static friction. So I'm going to match that with the centripetal force. So the centripetal force, I'll call that Fc. That's going to be mass times acceleration with Newton's second law. And that's going to be mv squared over r when we replace acceleration with the centripetal acceleration formula. So what I'm going to do is set these forces equal to each other, because static friction is the centripetal force. So set them equal to each other. I'll switch colors here. And that is why they did not give us the mass in this problem, because they cancel out. There's one on each side of the equation. Divide both sides by m, they cancel out. So I'm going to solve this for the speed. So it's going to be r will get multiplied to mu and g. And then I got a square root both sides. Plus or minus, but the minus is inadmissible. We're not going to have a negative speed. So what I'm solving for is the maximum centripetal force, basically. This is the maximum centripetal force that the table will possibly be able to provide this coin. And if it were to spin any faster, it would require a higher centripetal force, but it can't do it because there's only a maximum value for the static friction. That's why it will fall off the table if it gets any faster than this speed. All right, so that's coming out to be 1.5 meters per second.